Greetings friends, in today's lecture we want to look at what we call the calculus of variation, and under calculus of variation the most important part will be looking at what we call the Euler's equation. So how do we come up with the Euler's differential equation? We shall be saying that we can derive the Euler's differential equation when we have the condition for an integral that is having what we call an extreme value. So when we have an integral that have got an extreme value, then we shall be able to come up with what we call the Euler's differential equation. Now let us consider the function f. Let us consider the function f, which function is having variables y dash, then x, where this y dash will be representing what we call dy dx. So f is a function in terms of y, then y derivative and x. Now from there we shall consider an integral I, which integral I is an integration from 1 to 2 of the function f of y derivative and x, then dx. This I here, which is running from 1 to 2 of the function f of y derivative and x dx, will be considered where this 1 and 2 will be representing what we call the extreme points. So 1 and 2 will be representing the extreme points for the curve that will be represented by the Cartesian equation of y equaling to f of x. Let us consider some various curves from our extreme points 1 and 2. So when we have our extreme points 1 and 2, so we want to consider some curves. So starting from 1, we have that curve there. Then we have the curve running from 1 to 2. We have this other curve also running from 1 to 2. So when we have our curves from our extreme points 1 and 2, then we can say that these various curves can be represented by what we call the parametric equations, where we shall be considering the parametric alpha. Now the most important part that we shall use in our derivation will be for this the extreme of the integral in our equation 1. Remember our equation 1 was I, which is the integral from 1 to 2 f of y, then y derivative x dx. Now we shall be saying for the extreme of the integral in equation 1, its first derivative must be 0. You need to take note of this because we shall use it as we proceed in our derivation. So we shall first of all get the first derivative, then we equate the first derivative of this integral here to 0, such that we come up with the Euler's differential equation. So let us now consider the differentiation with respect to alpha on both sides of this given equation. So this equation here, we shall differentiate it with respect to alpha on both sides. Differentiating this function here with respect to alpha on both sides, we shall have del I, del alpha times the alpha, which is equal to integral from 1 to 2. So we are taking now, this is a function f with respect to y dash, then x. So we want to differentiate this with respect to alpha. Now we shall first of all consider f, where the variable now will be y first, such that we have del f del y times del y del alpha times the alpha, then plus we now consider when the y derivative is our variable, such that we have del f del y, then times, this is del y dash, times del y dash, del alpha, times the alpha, and for this case, times the x. Now, we are taking, but del x, del alpha is equal to 0, since you remember we had f with in terms of x, which is y. So y is f of x, and if y is equal to f of x, then it means we shall not be having variations in x. So that's why we shall consider del x, del alpha to be 0. Now, for that case, within this expression, we shall not be having del x, del alpha, since it will be containing, or it will be 0, so that expression will be eliminated, and we shall have our expression as that. Now, our next step, we shall have, let us consider integral from 1 to 2 del f del y times del y del alpha, the alpha, the whole of this is times dx, plus, I'm opening this bracket here, integral from 1 to 2 del f del y dash times del y dash del alpha times the alpha, the whole of this is into dx. What will this one give us? Let us maintain this one the way it is, maintain that the way it is, so we shall have plus integral from 1 to 2 del f del y dash times, let us try to simplify this. It will be del alpha times y dash is the y dx, then times the alpha times dx. Maintain this the way it is, then we shall have integral from 1 to 2 del alpha del y dash times, I want to have this one out such that I have d dx of, now it will be del y, then this one will be del alpha. We are having times the alpha times dx. So that is what we have. So generally we are at this given point where we have del I del alpha times the alpha is equal to this expression here. So we are calling this expression as equation star. Now from this equation star, I want us to first consider this part here. This part here is what we are considering first. Now this one here, this integral here will be equal to, consider this one as integration by parts. So you have this part here and this part here. So it means I will take this one as my u, so it will be del f del y dash times, I will integrate this to get del y del alpha, then from 1 to 2 minus integral from 1 to 2. So if this was taken as u, so it means it will be d dx of del f del y dash, then times this one here was taken as dv dx. So when we integrated this, we got del y del alpha, then it will be times the alpha dx. So that is what we have there. Now from this given point here, we shall substitute our limits. Remember, these are extreme points, 1 and 2 are extreme points. Now when you take the limits for del y del alpha from 1 to 2, this one will give us 0, since at the end points there are no variations. So when this one becomes 0, then it means the whole of this part will be 0. and we shall be left with that part there. So it means our expression now will become minus integral from 1 to 2 of d dx del f del y dash times del y dash del alpha, then times del alpha dx. To become, when we combine our results now together, our equation star becomes this. So we can write this one now be equation star star. Now we know that when you have del I del alpha times the alpha, that this one here is same as having the I, and when you have del y del alpha times the alpha, this one is also same as the y. So from our equation star star, we can now say that the I is actually same as integral from 1 to 2 del f del y times, when you look at this, we are saying that the whole of this one here is the y, so this one will be times the y, then there is dx minus integral from 1 to 2 d dx del f del y dash times, we are saying that this one here, the whole of this one here is same as the y, then times dx. So this one here will give us, I want us to combine this. We can realize that we have some parts or some common terms here. So dy dx, we have dy dx, so we can combine that and have integral of 1 to 2 into here we have del f del y minus d dx of del f del y dash into dy dx. So we have that. So we have with us di is same as integral from 1 to 2 of del f del y minus d dx of del f del y dash, the whole of this is into dx dy. So that is what we are having. But remember that for the extreme, the integral I, its the first derivative of the integral I must be 0. In other words, the I should be 0. For that case, it means integral from 1 to 2 of del f del y minus d dx of del f del y dash dx dy should be equal to what? Should be equal to 0. And for this case, this will imply that del f del y minus d dx of del f del y dash will be equal to 0. Clearly, when you integrate from 1 to 2 del f del y minus d dx of del f del y dash with respect to dx dy, we get 0. So it means the whole of this one here is equal to what? Is equal to 0. So because when you integrate this, you get 0, meaning that this one here is 0. So we shall be able to come up with this expression. And this one here is what we call the Euler's differential equation. So this is the Euler's differential. This is the Euler's differential equation. So thank you so much for keeping on TV Mashup. I wish you all the best, and we meet in our next lecture.
Yeah.